If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things that also really helps us out as well. Hi, welcome to another edition of Easy Theory. So we have an interesting problem which comes from the GATE 2020 exam. So this is GATE question number 42. It's actually written 32, but because there are 10 in the first part, I'm calling it 42. Most important number anyway. All right, so the question is, we have these two languages right here, and essentially what the question boils down to is what are these languages? Are they regular, context-free, or something else? So we have a language L1 here, which is WXYX, where each of the three pieces are just arbitrary non-empty 0, 1 strings. We know they're non-empty because of the plus up here. And L2 is XY, where X and Y are arbitrary strings. You can call this 0, 1. I'm going to call it AB because that's what the question said. The length of X is the same as the length of Y. So they're not completely arbitrary, but they have the same length. Okay, so you can say that all the strings in here are even length. And the two pieces are not the same. So this piece is not the same as this piece. Okay, so what I want to do is to arrive at the answer rather than just doing a process of elimination on the 4 possible answers. You could do that in a test situation, but I think I'd rather get down to the heart of things. Why is this true? So, and for one of them, L2 in particular, there's a part of it that I don't think exists on the internet, although I haven't looked very much. So it might be there, but I'm not sure. Okay, so let's look at L1 first. So let's look at L1. So this is saying that WXYX, so those are all the strings, and where WX and Y are not empty. Well, notice here that the W and the Y piece of the string, there's no condition on them whatsoever in terms of what they are in the string, other than that they're non-empty. The only constraint, so to speak, is the X part, which is repeated. And you maybe think, okay, well, it can't be regular because it's the same piece twice. And I remember from your other videos, Ryan, that if you have a string twice, then that's not even context free. And then therefore that's all you need to do. But I want to show you that this is in fact regular, which is actually a little surprising. So this is actually kind of a trick question, so to speak. So why is this the case? So notice that the X string could be anything. The only constraint is that it has to be appearing twice in the string, but it could be anything. So what we could do, for example, is say, well, let's just say, for example, X is 0, 1, just as an example. And then let's let W and Y be something. So W, let's say, is 0, 1, 1. And let's say that Y is 1, 0, 0. I'm just making this up off the top of my head. So if we just plug the pieces into the string, what we get is the W part first, so 0, 1, 1. Then the X part, which is 0, 1. I'm going to put a little space in between. The Y part, which is 1, 0, 0. And the X part, again, which is 0, 1. Okay, that's fair enough. But, so the decomposition, so to speak, well, let me do yellow here. So the decomposition is looking like this. So here we have the W part, the X part, Y part, and an X part again. But notice that because the W and the Y part can be anything, I can also break it up like this. And let me use a different color here. Like this. So this part is the, sorry, not X. This is the W part. This is the Y part. And these two are the X part. And why is this significant? Well, notice that if we had the same string in both cases, I can, without loss of generality, change the meaning of X to be the last character of both. So what this really boils down to is, If a string ends with a 1 in it, then it must contain a 1 somewhere else, because for everything else in the string, I just defined the first part before that first one to be the W part and the part in between to be the Y part. So let's actually pictorially look at what this means. So if the 1 is ending the string, then the requirement is saying that a 1 appears earlier. So a 1 appears somewhere else, and there may be stuff even before that. What I'm going to do is I'm going to call this part right here to be the W part, and this part right here to be the Y part. Then the X is going to be exactly the same in both cases. And the same situation holds if it ends with a 0. And we don't need to handle any other case because there's no other characters, and all 3 of the pieces have to be non-empty, so I don't have to handle the empty string, although that doesn't really matter for regularity purposes. So this question really boils down to is saying, if it ends with a 1, it has a 1 somewhere else, and if it ends with a 0, it has a 0 somewhere else. And that's very easily shown to be regular, because you can actually just make a simple regex for it. So this is saying, let's see, so if it ends with a 1, then it has to have stuff before it. It could be anything, so sigma star. And then it has to have a 1 somewhere, and anything could appear even before that. Then union, this exact same thing, essentially, but with zeros instead. And in fact, that's the regular expression for it. Actually, there's some restriction here. It's not exactly this, because we need to have that the sigmas right here need to have at least 2 characters in total. Actually, they need to be both non-empty. So actually what I should do here is to make these sigma plus instead. That would be a way to fix it. But yeah, these are the regexes for it. And because they're regexes and I'm doing a union between them, the result is clearly regular. So we can say that L1 is in fact regular. Okay, so now let's do L2, which is significantly harder than L1. So let's make some room for this. Dun, dun, dun. Okay, so how do we handle this one? So what I'm going to actually convince you right here is that L2 is not regular, but is context-free. So how in the world would you even show this? So I did this on the live stream this past Sunday, and I didn't know how to show that it was context-free, but I figured it out by looking into it further. But I showed it was not regular on the stream, and it was actually very difficult to show. It uses something called the P factorial trick, and I'll link a video to it down in the video description. And the reason it's so difficult is this part right here. So this part right here is not actually really difficult to handle. It's this part that's difficult. So the reason it's so difficult is that if I want to show that it's not regular, then I have to start with the 2 pieces being not the same, and then pump into the string enough to where they become the same. I can't necessarily escape this condition, because the amount of stuff that I put into the string might be an even length, and this just says essentially that the lengths are even. It says a little more, but effectively what we need is that it's even. This part is what's difficult about it. And we can't really show that it's regular. The intuitive reason is that if you have 2 pieces that are effectively the same, except that they have 1 character that are different, how would you be able to record that in the states? So that's the basic idea behind the intuitive reason why it's not regular. But how would you actually formally show it is actually really difficult. And if you have a single character alphabet, then this would be regular for an entirely different reason. But we have to be able to exploit the fact that there are two characters at play here. So if I just have like x be all one character, y be all one character, well, let's just actually look at that. So if so we're going to be using the pumping lemma here, if you haven't guessed by now. So we're going to choose, so this is a bad string, don't pick this string. So let's say a to the p, b to the p. And so my students mess this up sometimes. They say, okay, well, this part clearly must be the x part, this part must clearly be the y part. But notice that that's not necessarily the case unless we assume that the two parts have equal length, which they do. So it must be the case that the x part is right here and the y part is right here. And clearly the two halves are different, so I don't need to convince you of that. But notice that for purposes of pumping into the string, we're only going to hit these a's right here. So if I put more a's into the string, then it'll never be the case that x is equal to y. Why? Because the x part, because we're putting more a's into the string, the first half of the string only contains a's and the second half contains some number of b's. Even if the second half has a's in it, it still has b's, whereas the first half doesn't have a single b. So they still can't be the same. If we want to escape the language to show that it's not regular, we have to arrive at a string where the two halves are in fact the same. So that's significantly harder. So yeah, so don't actually do this. So don't pick that string. So I'm just going to tell you, so put into the comments before you watch the rest of this, what you think the string should be. So I'll wait. Okay, so I've waited long enough. So here's the string that you should pick. So it's going to be a to the p, b to the p, so same as before. But now what we're going to have is a to the p plus p factorial b to the p. And you think, what in the hell? So the reason for this right here is so that we're allowed to pump enough to where the number of a's at the beginning, because that's where we're going to be putting more a's in, is going to be the same as the number of a's here. And crucially note that these two runs of b's are exactly the same length. And that's never going to change because the only part we're going to pump is in the a's. Okay, so we're only pumping here, and so we're going to put more a's in. We'll see how many. And here, the number of a's here is going to be the same. So we're only going to modify this section, and the b's are going to be the same. So effectively, these runs of b's are effectively separating the two sets of a's right here, which is going to really help us. All right, so what we need to do is to look at any possible decomposition. So look at all possible decompositions. And what we know is that for the three pieces x, y, and z, so x is equal to some number of a's, I'm going to say alpha of them. Y is going to have another set of a's, oops, not alpha, it's going to be a to the, I'm going to call it beta, and note that beta is at least 1 because y has to be non-empty, the repeating part. And I'm not going to write it all down. I'm going to say z is the rest of the string. Okay, it's whatever's left over because that's the last piece. So, but I don't know how many times I need to pump into the string. So what I'm going to do is I'm going to look at this in the general case. What is x, y to the I, z? Because it says, the pumping lemma says that if it were regular, this string would always be in the language no matter what happens. So if I find a single value of I for which we leave the language, then that would violate that condition, and so it can't be regular. So what is this string? So I'm going to put I copies of this into the string. So I'm not going to do the math, but effectively what happens is that we'll have x to the power, not x. I'm going to have some number of a's, which is p plus I minus 1 times beta. And then we still have the run of PBs right there. Then we have, in fact, we have all the rest here. So none of the rest is going to be modified. It's just this part at the beginning. So the only way that this string can't be in the language is if these two halves right here are the same. So if this is equal to this. And clearly that's obviously going to happen if the number of A's right here is the number of A's right here, because the run of B's is the same. So yes. So this is not in L if and only if P plus, so the exponent on the first part is equal to the exponent on the second run of A's right here. So then let's just simplify this a little bit. So we have a plus P on both sides. Oops, didn't mean to do that. So the P's are going to get canceled right here. So then we'll have I minus 1 beta, or times beta, is equal to P factorial. And then if and only if, so if you simplify this, what you get is 1 plus P factorial over beta, is what that equation evaluates to. And I claim that this part right here is an integer. Why is that? Well, we know that beta is at most P, but it's at least 1 also. So it's some number between 1 and P. You see why this works? Because beta is between 1 and P, it must divide P factorial, because that's the product of 1 times 2 times 3 times all the way up to P. So beta divides it, and so this part is an integer, and clearly this is an integer. So I, right here, is some integer that we can pick. And in fact, if you plug this in back into the string that we got, for this value of I, we will get that the two halves are the same. And so therefore, if we choose this value of I right here, we leave the language. And so this tells us that L2 is not regular. I call it L in several other places. You know what language I mean. Okay, so this is a use of the P factorial trick. Okay, all right. So how do you actually, so that shows that it's not regular, but it very well might not be context-free either. We haven't covered the pumping lemma for context-free languages on the channel yet. We will eventually, but I want to show that it's it is context-free. So this is actually pretty difficult to show. And I wasn't able to do it on the stream because I haven't actually seen the language before. And it's actually pretty difficult. So how do you actually show that it's context-free? So let's actually try to visualize it a little bit. So if we have, like, say, A, B, B, A as the X part, and we have A, B, I don't know, A like this, and those be that would be the Y part. Well, notice that they only differ in one character. So the important thing to realize here is that they differ in at least one place, and that one place is the exact same index in both places. That's a necessary and sufficient condition for two strings to be different. They differ in one place at least, and that one of those places has the exact same index, okay, into the string. So this is the third character in this half, this is the third character in this half, okay? So the thing is, well, if you try to think of a PDA for this, as an example, you would have to try to push these onto the stack, or at least that's one way to do it, push these onto the stack. Well, then this A is at the top of the stack, and if you wanted to match it, the A that you want to match it with is way over here, not over here. And you can't just flip half of the string around in order for this to work. So we have to be a little bit smarter about this. All right, so how do you actually do this? So this is actually pretty cool. So What we're going to do here is we're going to uh, do the following. So I'm going to have a grammar right here. Let's change this to yellow. So let's make a grammar for this. So I'm going to have a start variable right here. And what we notice is that there are exactly 2 characters in the language. Well, then that means that one of the halves in the place where they're different, so to speak, in the place that they're different, one of the 2 halves has an A in it, and the other one has a B, because they must be different in that place. And I don't know whether the A one occurs first or the B one occurs first, but let's handle both cases. So I'm going to have 2 variables here, so A and B. And I'm going to have the A one right here eventually produce a single A, and the B one eventually produce a single B, and hopefully they're in the exact same location. And similarly over here, so if the B one occurs first, that's where it's going to be here, and the A one is going to occur here. All right, so what are they going to do? So they're going to do the following. So A is going to actually produce anything as long as it has an odd number of characters. As long as the middle character of the string, or so to speak, of what's produced by the A part, it has a in the middle. So it's going to have A, or it's going to have either 2 A's on both sides, 2 B's on both sides, an A and a B, or a B and an A. So it's going to look like this. And it may seem completely silly that we're doing this. Or B, A, B. Okay. So you may think, okay, well, this has absolutely nothing to do with this language, because the part where it's different has to be exactly in the same place in both pieces. But if we have 2 arbitrary variables like this, they don't have to be in exactly the same place, right? Yeah, they absolutely don't have to be in the same place. But we're going to see that it's kind of a trick question in some sense. And if you guess, the B variable is going to do almost exactly the same thing, except it's going to have a B in its middle. So it's going to have a BA, oops, I'm trying to match them so they're the same. So A, B, little b, B, big B, A, little b, big B, little b. Okay, so what we can notice here is that let's say that this is the part that the A variable produces, and this part is the part that the B variable produces. And they do not have to be the same length. They absolutely don't. But we'll see a technique to kind of show that there is a way to manipulate it so that it is. So here I'm saying that this part right here is what the B variable makes. This part right here is what the A variable makes. And in the middle of both of them, so this part must have an A exactly in its middle, and this one must have a B exactly in its middle. Okay, so, but of course the number of characters on both sides can be anything at all, right? Because I can apply any number of the B rules, any number of the A rules, and those numbers have nothing to do with each other whatsoever. So let's just call these parts, the lengths of these parts a certain name. So I'm going to call this K characters. And by the definition of the A variable, this part on the right side must also have K characters. So this one has K characters too. And again, the B side can have any number. So let's go with pink this time. So this part, I'm going to call L characters. It's a scripty L. And of course, on this side, there also are L characters. But the key is that the A and the B variable are exactly in the middle of both. All right, so let's actually define what the language of this thing is, what this language is. So the language, so to speak, is going to be, it turns out, is W1, then X, then W2, then what we have, V1, I'm going to call it V1, Y, V2. And what are the conditions here? Well, the sides on both sides of the W right here have to have the exact same length. So W1 is equal to W2, but they do not have to be the same at all, right? Because we had these other rules where it produced the other sides of the A variable could be different, or they could be the same. So, but we know that they have the same length for sure. So I'm going to call that length K, of course. And what we have, of course, is that the V1 is equal to V2, which is also equal to L. And what we also know is that the X part and the Y part are single characters and are not the same. So we have the length of X is the same as the length of Y, which is 1, and X is not equal to Y. And that's it. Okay, so what do we actually do here? So the key here for this question is to look at these two pieces right in the middle. So notice something interesting. So I can actually swap the two. I can swap the V1 and the W2. And you would get exactly the same thing. So it turns out that because you can actually swap where the two actually are, you can actually prove by induction, double induction, on X and Y right here, via case distinction and other things, although it's not really easy to prove, but you can prove that because the W2 and the V1 can exchange the characters right here, it turns out that that forces the X and Y to be in exactly the same position. So, let me use white. So, because W2 and not Y1, V1 can exchange characters, X and Y must have the same position. And then therefore, that forces that there's a difference in the two halves. And because we're just exchanging characters among here and not exchanging the V1 and V2 and W1, that means that we have the two halves having exactly the same length because they're in the exact same position. And we're only switching characters from a single segment in the string. And then that forces X and Y to have different characters in exactly the same position, which is exactly what the language asks for. And so from this, what we can determine is that L is in fact equal to L2. And that consequently shows that the language is in fact context-free. So hopefully that was really interesting. Leave comments down below if you have any questions or any other ideas about this particular question. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, I'll see you next time.